So now we'll go to a logistic regression model. It's going to follow the same pattern. It's pretty simple. Do you have a question?
Sorry. So the blue boxes are really pretty, but will it always be that the good predictions are in those corners and the bad predictions are in those corners, so we can just, if we don't have the code that makes the blue box thing work, we can just know, okay, it's the top left and bottom right corner.
Yeah, let me respond to that question. Generally that's true, but some tools won't give them to you in that order. They'll always tell you these were the predicted versus the actuals, and you can go in and say, okay, that's a true positive and that's a false positive. But some tools will just they'll just go like this. You know what I mean? So you should learn beyond just the diagonal pattern.
Mm-hmm.
You should say, okay, what's a false positive? What's a true positive? Because some tools you'll get in work or you'll get in your internships, and they'll just give it the right information in a different order. And so you'll just say, so you got to kind of just figure out what it is.
Okay.
Mm-hmm.
Yeah.
Yeah, and someone in the previous class asked about like, well, what if there's even more states that you could predict? Like, I think there's a sample data set in a lot of tutorials called the iris data set where there's 3 different types of flowers and you can predict which type of flower it is based on the petal. And so if you have 3 different things you're trying to predict that it could be, then you'll have like a 3 by 3 grid. And so you do want to look at the labels, like just matching up what you predicted versus what the actual was. So yeah, it's a good point.
So is that reflected in the order of the target names when you call the function?
Yeah.
0 would be the first, 1 would be the second, and 3, 4 would be.
Yeah.
So we put like as target name to not survive because 0 equals to not survive.
Yeah.
Yes. Yes.
So now we'll go through a logistic regression model. It's basically the same steps, except for we're importing the logistic regression type model. We're going to fit it the same way. And you can add other settings in this when you're creating the instance of the model that we'll probably go over later. We make our predictions, and then let's see. We'll see how well we did. So we can compare our precision and recall. So we got 80%, 86% here on this model versus 68 and 77. So we did a bit better with this logistic regression model. So as you go along, you'll have to learn, just kind of play around with the different models. Some of them work better in some situations, some work better in others. So these were using all of the predictor columns. We kept them all in for these ones. And then the confusion matrix, we'll show the prettier version so we can see. Like on the KNN, I think it was like about 70, 75 on these 2 down here, but we got a lot more in the correct box here. So the logistic regression did a little bit better. So now let's try the same step with a bit fewer variables, because sometimes we want to avoid overfitting our model. I think you talked about that earlier in the semester. So sometimes we want to take away a few variables and see if we can still get about the same predicted power, so we're not making sure we're not overfitting. So we'll do that. We'll make a new data set where we just include the passenger class and the title. And we'll do the same process of partitioning the data, making a new logistic regression model and fitting it, and then we can see how well we did. Let's see. Oh, I don't think this worked, because that looked the same. So we can see that we lost a little bit of predictive power because we took away some of the variables, so we might want to put those back in. But that's just something to think about as we're going through this. And then we'll do one more with the decision tree or cart method. We'll just use the passenger class, the age, and the sex. And we'll partition. We'll make the model. We'll run our predictions. And I'll go over this at the end. We'll see how well we did. 76%, 84%. So I don't think that was quite as good as a logistic regression. And again, we did use less variables. So, question over here.
Oh, I thought you were questioning about me.
Yeah.
You just mentioned earlier that you were worried about like overfitting, and that's why like the values were high. So then you took out a couple variables and they were lower, obviously.
Mhm.
How do you know that it's not like how come it's not overfitting? Does that make
Well,
sense?
you have to try to reduce some of the variables, the predictors, and see if things get better or worse. Sometimes a bad set of predictors are confusing the learning models, and so when you get rid of them, the model actually gets better. It's a little counterintuitive, but and then other times, like here, you drop some variables and the outcomes get a little bit better, or get a little bit worse because there was some predictive, helpful, unique information in those ones that you dropped. And the only way to know is to try it, is to drop some and see if it helps or if it gets worse. In this case, it got worse, so we put them back in. Yeah.
Yeah, another thing to consider is if you're implementing this machine learning in some big system where you've got tons and tons of data coming through, sometimes you may want something that's maybe slightly less predictive, but is a lot simpler because you're using less variables, so that every time you're trying to predict something, if with all these volumes and volumes of data coming through, you want something simpler so it can actually spit out things quickly. So that's just another thing to consider. And also, sometimes your management wants to be able to understand the model, and so if you've got a million different variables in it, it's kind of hard to explain. So that's just another couple of things to consider about that. So with the decision tree, I mean, you're going to go more of this on Wednesday. There is a way for you to kind of create a visualization of what the tree looks like. Um, and so basically you can see like at each of these nodes, it's going to basically you'll split the data in one way or another. I can zoom in. So like, just for example, like if the first node could be something like if the age is less than 25, go down this path. If the age is greater than 25, go down this path. And so it'll go down all these splits, so that at the end you'll be able to predict if when a new prediction comes in, it'll just go through each of these splits and see which is true and which is false. And when you get down to the end, it'll see what the actual value is. So there's a way for you to visualize what the decision tree looks like. And again, you'll go more over this next class, how to interpret these things. But being able to see this is kind of, we've had some trouble making it work. But you have to go to your Anaconda command prompt and you install Python graph viz and then you install py.plus. I had to do it in that order. For be able to use this code to create the decision tree. Some people have had some issues with trying to make it work. I had to actually like uninstall Anaconda and reinstall it and do it in this order for it to work, but that's just something that we can try. So.
Yeah, don't just do it with pip. Do it with conda. Go to your terminal prompt and run those. And as you run those two commands, then this conda install Python graph is. You'll see the little thing saying I'm working, and then it will finish the install. Then you'll do the next one, and so that it can bring in the library that will create the nice looking trees.
Because there's also some dependencies for these, and I think Conda will go find those and bring them in.
Yeah,
So.
Conda's better than pip because Conda gets everything that is needed.
Mm-hmm. So that's kind of a high-level overview of how modeling works in Python. You can do simple models pretty easily. It's just you fit the model, predict it, and you can see how well you're doing. So I guess that's mainly what I have. Is there any questions about how this all works?
Could you review the concept of the like the naive model?
Mm-hmm.
You did that.
Yeah. Let's see. So basically, you're going to assume that whatever the majority status is, like more people didn't survive than actually survived, you're going to assume that everybody didn't survive. And so we've got 891 total records, and we've got 549 who didn't survive. And so if we assumed that everybody didn't survive, we're going to be correct 62% of the time. and that's our base model. We're going to hope that our new models that we build will help us be better than 62% correct, if that makes sense.
The reason they call that the naive model